Good morning, and thank you for giving us this opportunity to share our research. And thanks for the attendees for attending my presentation about a coil array using cone-shaped structure for safe deep brain stimulation. So my name is Rawan, as you said, from the School of Information Technology and Electrical Engineering, University of Queensland, supervised by Professor Amin Aboush, Dr. Ahmed Taha Mubashir, and Professor Firuz Zara. Today in my presentation, I will go through the introduction, which I feel like it's now kind of trivial for most of you as scientists or like science background. But I will go fast through it. The methodology used in this study and our outcomes, and finally the conclusions. So the rationale of my research was that since the first case was diagnosed with Alzheimer's disease 120 years ago by Dr. Always Alzheimer, when he found the strange plaques and tangles in her brain, until now we still can't prevent, cure, or at least slow down the progress of Alzheimer's disease. And we found that one of the main reasons for that is a presence of a natural barrier in the brain called the blood-brain barrier that complicates medication delivery. So we start thinking from an engineering background. So we looked first at the Alzheimer's brain, and we noticed that Alzheimer's starts at the neuron's point of connection, which called the synapse. The accumulation of the plaques, amyloid beta plaques between the synapses disrupt the neurotransmission, causing cell death and hence brain shrinkage. So if we want to think about a way to restore Alzheimer's brain, we will think about creating or strengthening a new neural connection and new synapses. And we found this is possible by what we call the neuroplasticity, which is the ability the ability of the brain to form a new neural connection with response to stimuli. So if we stimulate or exercise virtually the brain, we could get a bulkier neural connection. And this could be happened by either a natural way, like learning a new thing, making new friends, etc., or by a synthetic way, which is the brain stimulation. And here we will start thinking about brain stimulation. When we looked at Alzheimer's brain, we noticed that the first affected region of the brain is the hippocampus, which is responsible for forming new memories and processing the long-term memories. But it was like a deep region of the brain because it lies 4 to 6 centimeters from the skull. So the current TMS or the current non-invasive brain stimulation techniques have a poor performance in the deep region of the brain, and only invasive ways are used for deep brain stimulation. Our target was to stimulate a deep region of the brain like the hippocampus non-invasively. And we know that we think about TMS, the most common like form or used of brain stimulation, as it's a non-invasive way and have many like let's say advantages rather than other non-invasive stimulation techniques. But we know that the main challenge in TMS is to overcome the trade-off between stimulation depth and focality. So our goal was to find a coil geometry that has a slow attenuation rate, study adding a ferromagnetic structure like a core or shielding around this coil, and also to try to design a TMS device for safe, non-invasive deep brain stimulation. And here, when I say safe deep brain stimulation, what I mean like I want the electric field at the targeted area, like the hippocampus here, to reach the threshold value for stimulation. And at the same time, I don't want the electric field to exceed the safety limit at a cortical region like the gray matter. So I will call this ratio, which is E gray matter over E hippocampus, the safe ratio. And according to the guidelines, this should not exceed 2.2 value. The methodology of our study, we use a realistic simulation environment called Sim4Life to calculate the electric and magnetic field with a high fidelity head phantom called MEDA that includes 115 different structure with a detailed characteristic for deep brain region, which we were looking for the hippocampus region. So we used two coil geometries. The first one called the magnetic resonance coupling, MRC, and the second one that we designed is a cone-shaped coil, lies in three different layers to slow the attenuation through the brain. We studied the effects of adding a magnetic core to concentrate the field at the middle of the coil, and also a magnetic shield to seal the field in, and hence reduce the focality, or enhance, sorry, the focality of the system. So for the coil position, we put it in the closest point to the hippocampus, targeted hippocampus region. Results and discussion. So for the result, we have noticed that using the magnetic core and the shielding enhance the field value and also the focality of the field. On the other hand, if we do the simulation using by adding a hand, like the operator hand, we noticed that using the shielding will reduce the field dramatically at the hand, which enhance the safety of the operator. And we also did a parametric sweep to see the effects of the size of the coil. And we have noticed, like we all know, that bigger size will offer the deeper stimulation or penetration through the brain. However, we have noticed that after a certain size, the ratio between the field at the gray matter and the hippocampus will get to saturate. So we decided to use like a size between 50 to 60 millimeters radius. But also, like using one coil, it was impossible to reach the hippocampus safely. So we decided to use an array of electromagnetic coils and a proper arrangement around the head. So each of these coils will contribute with a part of the electric field to reach the hippocampus without increasing the field at the gray matter above the safety limits. We study many geometries, and we find, like, by using the coil that we have decided to use, we will get close ratio to the one that we need. The best orientation was when we arrange the coils tangential to the head toward the targeted region, which is the hippocampus, but it was kind of random arrangement. So we decide, or we try to organize this in a way to be like easy to fabricate, and at the same time still have the safety limits for the deep brain stimulation. And we got good results.
When we need to wrap up here, Rawan.
Sorry.
We need to wrap up. Yeah.
Okay. Yes. When we when we did the experimental testing, we also get a nice result, but we still need to do another stage of simulation, experimental testing by using a higher current, because our current was a little bit low, what we have at our labs. So in conclusion, we can say ferromagnetic structure improves the performance of the coil, and also coil array could reduce the field at cortical region with respect to deep region of the brain. Thank you.
Great, good work. I'm afraid we don't really have any time for questions. Just a quick question, Rawan, more about the choice of Alzheimer's disease and targeting the hippocampus given that Alzheimer's is more of a generalized disorder? Was there a particular reason
Yes.
for that?
So actually, so the array is a promising treatment not only for Alzheimer's disease, for many other neuropsychiatric disorders. But our rationale was Alzheimer's disease. But when we start working on the project, we noticed that it's like a kind of target for many other neuropsychiatric disorders. I'm not sure if I understand your question properly.
Great, thank you very much.